Okay, in fact, this is the example that I used to do in the class, but it has quite dramatic problem, okay, especially when we try to find the maximum moment of this beam, because the beam is rather short. See, it's only 20 meters long, and the length of the load, now you see it's like 6, 11, 15, 17. So when I try to place the load to get the maximum moment, you know, if I try to place in the center, either load number 1 goes off or load number 6 never reaches the beam. So I have to change the load to get the Q, because starting from having a Q equal to the summation of these 6 loads, you know, we result in either load number 1, when you place the load group, load number 1 is falling off, or load number 6 is falling off. So I say this year I'm going to change the examples because I don't want to explain about that. It's kind of a long explanation, and I think it creates confusion rather than better understanding. So I decided to change the example, but we're not going to use this to talk about moment. Okay, the reason I say before. So let's say, in fact, the question is for the maximum placement for Vmax at the location 6 meters from left. Okay, so say now that's not much we can do. We have to keep on, you know, placing the load. Now, you know, because the point of interest now is at 6 meters from the left. So your inference line for the shear would look like this. Okay, and that would be again at the location 6 meters. So the height here would be 6/20, right? Minus 6/20, that's 14/20. Just take the ratio, because here is always 1. The change of shear at this location, all right? Make it look more beautiful. So now, because I don't know what's going on, so I'm just going to place load number 1. First case, I will replace, load number 1 at, say, this location. Let's call it point C, okay? Otherwise, I would have to call it by a long name. Replace load number 1 at C by load number 2. So what we usually have is like this. Load number 1, and then we move everything to the right, to the left, so that load number 2 replaces load number 1 at C. Okay, can you guys see that? So now load number 2 is 4 meters away from load number 1. So that means everything moves 4 meters, right? Okay, and when load number 1 is at this location, I think that is 14 meters. So when load number 1 is on this, do we have load number 6 here already? Let me check. Okay, we only have, that's a difficulty of it, yeah. From load number 1 to number 4, that's 4 plus 2 plus 5, so that's 11 meters. And then load number 5 will be 15 meters away from load number 1. So when we have load number 1 at C, load number 5 is not on the beam yet. How do you like that? Okay, so when we move everything to the left, okay, And so that load number 2 replaces load number 1 here at C. When that happens, because load number 2 is here, and then this is 2 meters plus 5, that's 7, that's 11, so that's 13. Load number 6 is 13 meters away from load number 2. So this movement will cause load number 5 and 6 to appear on the beam. And load number 1 is now down here. So how do you like that? Now it's kind of, create more trouble for you. So from this, when load number 1 is at C, we have load number 1, 2, 3, and 4 on the beam. So with the movement to replace load number 1 by number 2 at C, now the first case is that load number 1 through 4 move up with load number 1 in the air. So I can say now load number 1 is like 2, right? 2992. 2 plus 9 plus 9 plus 2. They all move 4 meters, right? Because the load number 2 and number 1, they are 4 meters apart. And the slope is 120. But because load number 1 is in the air, so I'm minus 2. Take it out. And then second, that's the first one. 5 and 6 are now on the beam. So we must add the presence of load number 5 and 6 on the beam. Okay? So now when 2 are here, because load number 2 to 5, so you see 2, 5, and 4, that's 9 meters. So load number 5 here, the distance from load number 2 to number 5 is, what did I say? 11 meters, right? And then it's load number 5. And then for load number 6, this distance is 13 meters. So the presence of load number 5 will give us a positive shear equal to the load itself is 9 tons. And this ordinate is, that is 14.20. That's the height, correct? That this height is 14/20. Now, that is also 14 meters long, but load number 5 from load number 2, it's 11. So that this distance is 3, correct? So that has to be multiplied by 3/14. And then load number 6, it's 9 tons as well. The value here is 14/20. And then this distance, if that's 13, so that's 1. It's 1/14. See how 14 cancel each other out nicely. So that's delta shear when 2 replaces 1 is equal to that number. This is like 20, right? 20 multiplied by 4 divided by 20 minus 2. That's 2. And that one, 9 multiplied by 3/20 plus 1/, that's 1, so that's 4/20, right? That's 1.8. Okay, doesn't seem to match the number that I have before. But that's the idea. What did I miss? Okay. But yeah, let me okay, so that's no, that's sorry, that's 22. 22 multiplied by 4 divided by 20 minus 2. That's a 2.4. Okay, so that's the 1.8, right? So that has to be 4.2 tons. Okay, so now we know that by moving load number 2 to replace load number 1 at C, the shear would increase 4.2 tons. So one more thing that we should do, because we want a placement that will give us the maximum shear, so we have to keep doing it. So now I'm going to move load number 3 to replace load number 2. So in the beginning we have this, but now we know 6 is here and 1 is there. Now we're going to move 3 to replace 2 there. So now 3 will be here. Since 6 is there, so 6 must be there. 2 is now down here. And 1. We need to check whether or not 1 will still be on the beam. Okay. So in order for 3 to replace 2 at C, you know, they are 2 meters apart. So the whole thing moves 2 meters, right? Okay. So now before that, this is 6 meters, correct? And now load number 1 and number 2, they are 4 meters apart. Everything moves 2 meters. So load number 1 just sit there at the 0 value. Okay, so it's nicely done, because you can say it's still on the beam, you know, and you can consider the load number 1 moving up the slope and sits there. So you can now say load number, what did I say? Okay. Load number 1 through number 6. Everybody moves up except 2 that is in the air. I keep mispronouncing this word, right? Okay, so this will be easier. So I can say delta V, when this happens, is that everyone moves up the slope, and let's say the load would be 2 plus 9 plus 9 plus 9 plus 9 plus, oops, sorry, fourth one is 2, right? The slope is 150 and everybody moves 2 meters. Okay, so everybody gives the positive value except the 2 now is in the air, so we need to bring 2 down. Load number 2 is 9, so it's minus 9. And the total here is, load is total 40 divided by 50 multiplied by 2 minus 9. So that's what? You don't get the same number. Oh, that's a 20, right? 50 is from the previous problem. That's why. Okay. So it's -5. So you see, now when load number 3 moves in to replace load number 2 at C, the shear at C decreases by 5 tons. So you can say, because when load number 2 moves in to replace load number 1 at C, your delta shear increases by 4.2 tons. But when load number 3 comes in and replaces load number 2, now our delta shear decreases by 5 tons. So you can say it may be concluded that placing load number 2 at C gives maximum force, shear force at C as a result. Okay. But you may argue that should we keep doing this? But when you keep doing this, you know, load number 1 will leave the beam, and then probably load number 2 as well. So you have less number of loads acting on the beam once you try to move load number 4 to replace load number 3, and so on. So chances are, by observation, this is the condition that gives us the maximum shear at C. Okay. So is this more difficult?
Yes.
Example, you know, see how things move. Okay. So is there any question?
Teacher, my not come from the load at
because load number 2, if we move load number 2 up, it's now in the air.
Oh, okay, sir.
Easier to do that, right? So it's not in fact difficult, you know. Let's say if this is not the influence line, you play the games by moving the balls up the slope and see how the values change. It's just like simple as that, right? So is there any question? I don't want to do the maximum moment because you know, it will cause some confusion, because in order to get the maximum moment here, all the loads are not on the beam. We have to miss load number 1 because it's the smallest number. Get rid of this, and when 2, 3, 4, 5, 6 are on the beam, that's where we're gonna get the maximum moment. But yeah, right. So, any question, folks? You want me to do the maximum moment for the sake of it? One more?
Yeah, can or not?
Yeah, sure. But as I say, let's do it, okay? Because we have time. For M max, only loads 2 through 6 will be on the beam. So now, let's say we have load number, we have load number 2. No more copy option. Okay. Actually, I have the picture here. Okay, I can look in there. We have load number 2, 3, 4, 5, and 6. Okay, so this is a result of the trial and error. I've done it so many times to get this. So we can now say load number 1 will not be on the beam. Okay, so we now have to calculate for the Q. So let's say Q in this case, because this is 99299, right? So Q is 38 tons, right? And now I'm just going to take the moment here. It's going to take the moment here. Okay. Let's see. Okay. Now the X bar is going to be equal to the load number 3. Okay. The second one here, 9 multiplied by the distance from load number 2 to 3. That's 2 meters. Okay. And then load number 4, 2, that's 7 meters. Load number 5, 9, so 7, add 4 more, so that's 11. And load number 6 is 9, 11 plus 2, that's 13. Okay, divided by 38. So my X bar is where? 6.526 from load number 2. Okay, so that it's pretty much here, right in front of load number 4. And that distance is 6.526. And the distance from load number 2 to 4, that's 7 meters, right? Here is 7. So that leaves the gap for the center line, the beam, be here. Okay, about because the gap is very, very tiny, you know. Let's say how much? 7 minus 6.2526. That's only 0.747. It's like bone, right? So that gap is 0.474. So that means the distance from the center line of the beam to the Q is only half of that, which is 0.2368 if you're crazy about number. Okay, and then you have load number 4 here with the same distance, 0.2368. Okay, so we have the 20 meters long beam. So this distance is, load number 4 is now at the distance 20 meters. So that's 10, right? So the number 4 is 10.2368 from the left support, or I should say 237 is already crazy enough. So let's use only that. Okay. 237 has to have 7 because otherwise it'll be 24. So now I can place load number 3. 3 is 5 meters away from 4, so it becomes 5.237. And then load number 2 is minus 2 more, 3.237. Right, and then we have load number 5, which is 4 meters away from load number 4. So this becomes 14.237. And then load number 6 should be closer. 2 meters away. 16.237. Again, to calculate the reaction, you can easily use the Q, right? But don't forget that you have to add this, right? So reaction on the left is going to be equal to 38 multiplied by 6.526. That is the distance from the Q to load number 2. So we add 237 more. Okay, and then that's reaction on the right. On the left it has to be another one. Sorry, my bad again. Yeah, on the right. It's kind of easier. Divide by 20. So that would give us 18.55. Reaction on the left will be just opposite of this. Or you can just use sigma Fy if you're sure you're correct. 1945. And now, because we have 19, in order for the shear to become 0, you have to reach load number 4, right? So that's where M max is going to occur. So V is going to be 0 at underneath load number 4. Okay, so as simple as that. M max is pretty easy. It may take a little long to calculate this, but you should know it's pretty straightforward. So it's 19.45. That's a reaction on the left. And the M max is right here underneath load number 4. So that means it multiplied by 10.237 minus load number 3. It's 9. Just 5 meters. How long? 5 meters away from load number 4, and then minus load number 2, another 9, and 7 meters. Okay, so that is 91.1 ton meter. You see, notice that load number 4 has to be placed just slightly off the center line to the right. So for those of you who do not know how to handle this, and then you decide to place load number 4 right there at the center line, you may get the number not so different from this, but that is fundamentally wrong. Okay, because we are doing this to obtain the load placement. So if you want to do that, you will not get much because you don't have the knowledge to place the load where it will hurt the beam the most. Okay, and then that's it. One more example. So you guys are pretty good to go. Any question? That's it, folks. Question. You want me to scroll this up and down or anything? Hello. That's it. Class is over. Oh, okay. Are you laughing or are you crying or are you in pain? It's hard to say. Okay, so if you don't have any question, let me stop the record first.